Okay, we're going to do number 41. I like this problem because it doesn't give you any numbers. It wants you to solve for an expression. So what it says is, an object of mass m swings in a horizontal circle on a string of length L that tilts downward at an angle of theta. Find an expression for the angular velocity omega. So we're trying to find omega. So this is the situation. It's like our tennis ball here, but instead of doing a vertical circle, you're doing a circle like this, so it kind of makes a cone. Okay? And then we know that angle, and we know the length of the string, and we want to be able to solve for what omega is. So this is all we got. But let's do our free body diagram, just like we always do here. So here's our free body diagram. We have gravity, of course, and we have tension. Let me make our angle a little bit better. All right, here we have tension going this way. And notice that we have this angle theta. That's the same as that angle, right? If I do it like this, those angles are the same because they're alternate interior angles of parallel lines. So these are going to be my axes. This is the x-axis, this is the y-axis, because it's going in a horizontal circle. So I need to take this component here, which is just t cosine theta, and this component is t sine theta. So far, so good. Now we're going to do f net x. F net x is going to be equal to minus t cosine theta. That's all we have. But that's the direction it's going in a circle. So that has to be the centripetal acceleration. So this becomes negative mv squared over r is equal to negative t cosine theta. The negatives cancel out. You end up with mv squared over r is equal to t cosine theta. Now we don't know theta, we don't know t, so we can't solve that. But we have f net y. So if we do f net y, we have t sine theta positive minus mg, which is negative. This is equal to 0, or we can say that mg is equal to t sine theta. And then we're going to solve this for t. So I'm just going to divide. I'm going to say, oh, t is just equal to mg over sine theta. Then I'm going to plug that back in to here. So I'm going to end up with mv squared over r is equal to mg over sine theta, that's t, times cosine theta. Okay? So far, so good. Now, this is where it gets a little tricky. First, we're going to divide by m, so the mass doesn't matter. But remember what v is. V is equal to omega r. So v squared is equal to omega squared r squared. So I'm going to plug that into there because what we really want is omega. So I'm going to end up with omega squared r squared over r is equal to g cosine theta over sine theta. Okay, and that cancels with one of those, so I end up with omega squared r is equal to g cosine theta over sine theta. Okay? But I don't want r in here. They didn't give me r, they gave me L. But I have to figure out what r is. R is this side right here. Right? That's the r. It's not L, it's this side here. But I know these, right? So I can say, oh, cosine theta is equal to adjacent over hypotenuse, which is just r over L. Or r is equal to L cosine theta. I can plug that into there, and so omega squared times L cosine theta is equal to g cosine theta over sine theta. Notice I divide both sides by cosine theta, that goes away. Now I'm going to solve it for omega, so what I end up with is omega squared, I'm going to move the L over this side, is going to be g over L sine theta, where omega is equal to the square root of g over L sine theta. That is your answer. So we got it in terms of g, which is a constant, L, and theta. That's all we need. Now for part B, they actually ask you to plug in numbers. Part B, we have a radius of, just a second, gotta find it here. 500 gram rock to a 1 meter long string, and it's at 10-degree angle. We don't care about the mass of it, it doesn't matter, so this is 9.8 over L, which is 1 meter times the sine of 10 degrees. We get omega is equal to 7.5 radians per second. But they want that in RPMs, so we have 60 seconds over a minute and 2 pi radians over a revolution. Remember, that cancels with that cancels with that. And we end up with a value of 72 revolutions per minute. Or a period of just less than a second. All right, and that's how you do number 41.